In this lecture, we will discuss the maximum modulus principle and minimum modulus principle. To prove maximum modulus principle, so first of all, we discuss a lemma, so that will be used in the maximum modulus principle. So what is the statement of the lemma? Suppose modulus of fz, suppose modulus of fz, which is modulus of fz less than equal to modulus of f of z naught. So at each point, z in some neighborhood, z minus z naught less than epsilon, in which the function f of z is analytic, then f of z has constant value f of z naught throughout the neighborhood, throughout the neighborhood. So in the given statement, the function modulus of fz is less than equal to f of z naught, and this function is analytic in the neighborhood of z naught. Then our aim is to prove that the function fz has constant value fz naught throughout the neighborhood. Now, proof of this lemma. So first, understand the statement. So if we discuss, these are the two-dimensional spaces. This is a origin, y-axis and x-axis. So this is a circle. So this is a circle. So if I write this is a circle contour C, and this is a z naught, and this distance is epsilon. So what is this? It is a neighborhood of z naught. So remember, with the radius epsilon. So this is a neighborhood of z naught. So it is denoted by C. And if I take, this is some point z1, and distance between these 2 points is r. Suppose this distance is r. So if I take the neighborhood of z naught with radius r, so then z1 is the point on the neighborhood. So this is denoted by CR. So this is a CR. So here R is less than epsilon. Now, by Gauss mean value theorem, so what is the Gauss mean value theorem? By Gauss mean value theorem, the f of z naught, which is equal to 1 by 2 pi 0 to 2 pi f of z naught plus r into e raised to power iota theta d theta, where 0 is lies between lies between 0 and 2 pi. So this is the equation number 1. This is the equation number 1. So it implies, so very modulus of fz naught. So this is equal to what its value? So this is a modulus of 1 by 2 pi integration 0 to 2 pi f of z naught plus r e raised to power iota theta into d theta and this values. So this is a modulus of this values. Simply substitute the value of this value. So this can be written as, it implies, which is f of z naught less than equal to 1 by 2 pi and this value 0 to 2 pi and modulus of f of z naught plus r e raised to power iota theta modulus into dz into d theta, so into d theta, these values. So this can be written as 0 to 2 pi modulus of fz naught into d theta, because this 2 pi is shifted to this side, which is less than equal to 0 to 2 pi f of z naught plus r e raised to power iota theta, its modulus into d theta. So this value. So this is a equation number, suppose 3. So this is equation number 3. From this, what we get? We get this is equation number 1 and this is a suppose equation number 2. Now this is equation number 2. Also in the given part, given part, modulus of f of z, which is less than equal to f of z naught. So it implies that modulus of f of z naught plus r e raised to power iota theta less than equal to modulus of f z naught, these values. Now it implies integration 0 to 2 pi f of z naught plus r e raised to power iota theta modulus into d theta less than equal to 0 to 2 pi modulus of f z naught into dz. So this is equation number 3. Now from equation number 2 and 3, we get left hand side and right hand side are equal from equation number 2 and 3. We get what we get? We get 0 to 2 pi bracket modulus of f z naught minus modulus of f z naught plus r e raised to power iota theta bracket 1 d theta, which is equal to 0. So this values. Now from this, since this integration is 0 and function is analytic, so this value is again equal to 0. So it implies modulus of fz, which is equal to minus, which is equal to f of z naught plus r e raised to power iota theta. This is for 0 less than equal to theta less than equal to 2 pi. So this value, so it from this integration, it implies this value. So what is this? This is a point z, nothing but this is a point z. So it implies f of z naught. And what is this? This is a some point z for all point for all point z on a circle on the circle CR. What is that? That is z minus z naught, which is equal to r. So this is for all this point. Then it implies this circle is lie between the neighborhood of z naught. So it implies f of z is equal to f of z naught. This is for every z in neighborhood z minus z naught less than epsilon. So this is applicable to every z in the neighborhood of z minus z naught less than epsilon. So it means it has the fixed value, it has the constant values for every point in the neighborhood. So remember this lemma. So what we conclude from this lemma, now what is the statement of the maximum modulus principle? So this is very important. So maximum modulus principle, maximum modulus principle. Now statement is, suppose a function fz, suppose a function f of z which is analytic but not constant, but not constant in a given domain, in a given domain D. So given function is analytic but not constant in a given domain D. So then modulus of fz has no maximum value, has no maximum value in D, value in domain D. So what it means? It means if it has maximum value, so this has maximum value on the domain D, not interior to the D. So what is the statement? If a function is analytic, number one, number two, not constant, then it has no maximum value in D. So remember that it has no maximum value inside the D. So this is very important result. Now, proof of the theorem. Just assume we will prove it with the help of contradiction. Now assume f of z, assume f of z has maximum value, has maximum value at some point, at some point z naught in D. So suppose it has maximum values z naught in D. What it means? It means f of z, modulus of f of z is equal to f of z naught. Now, if this point is, if this is some domain D and we define A, this is some point z naught, this is some point z naught, and this is a some polygon line. So we will find the polygon line. How we will find the polygon line in D? So we draw a polygon line L lying in D and extending from Z to Z naught to Zn such that Zk minus Zk minus 1 is less than D. So I first draw a polygon line. So for example, if I go to this and then to this and then to this. So this point is Z naught, this point is Z1 and next is Z2 and so on. Suppose here point is Zn minus 1 and this point is Zn. So what we will do? So we will do that we draw a, so I write here we draw a polygon line L. So we draw a polygon line L lying in a D, lying in a domain D and extending from Z naught to Zn such that difference between any 2 point is less than D, small d. So difference between these 2 points is less than small d, where k is running from 1 to so on up to n. It means this difference is less than d, and difference with next point is again less than d, and so on. Then and find a sequence of neighborhood, and in addition to that and find a sequence of neighborhood that is denoted by n and k. So this is a center zk and radius is d. So radius is d. So this is a set of all z such that z minus zk is less than d, and this is less than d. So we define a circle whose radius is less than d. So this values, they are equal to less than d. Now k is running from 0 to so on up to n. So it means we find this polygon line, and this value is z0 at z1 less than d. So here I define a neighborhood n0 whose radius is less than d. So this is some neighborhood whose radius is less than d. So this is denoted by n0. Now z1 is point inside this d. Now next define the neighborhood where center is z1 and again radius is d. So here I define this circle, and this is a neighborhood n1. So this is n0 and this is a n1. Similarly, in this case, so this is a n whose radius is d, and next is this is z n minus 1. So this is a neighborhood n minus 1. So what we see that this z1 belongs to previous neighborhood. z1 belongs to neighborhood n0. Similarly, z2 belongs to n1. So where what we see that z1 belongs to n0, z2 belongs to n1, and so on. In general, zk belongs to nk minus 1. Zk plus 1 belongs to nk. So what we did, so we draw a polygon line in such a way which satisfy this kind of sequence. Now we will apply the previous lemma. By previous lemma, this value f of z1 is equal to f of z0 because fz has maximum value at z0. So it means f of z1 is equal to f of z0. So we will apply the previous formula, the previous lemma at each place. Now since modulus of fz has maximum value at z0 point. So it has maximum value at z0 point. Then by previous lemma, lemma fz has constant value, fz has constant value, constant value f of z naught throughout n0. It means, it implies in particular f of z1, because z1 is inside it, is equal to f of z naught, this values. So this is a in particular. So in particular, so we get this values. Now in next neighborhood, so continue the process. If we continue the process f of z2, which is equal to f of z, which is equal to f of z1, f of z2, f of z3, f of zn minus 1, and this is equal to f of zn, this values, and all these value equal to f of z naught. So it implies f of z is constant. It implies f of z, which is equal to constant, because it has same values, so it is a constant. So which is contradiction, which is contradiction, hence our supposition is wrong. So our supposition is wrong. If our supposition is wrong, then if our supposition is wrong, so what we assume? We assume that fz has maximum value at some point z naught in D. If it is a wrong, then f of z has no maximum values, then it means f of z has no maximum value inside in D. So it has no maximum value inside D. So which prove the maximum modulus principle. Similarly, we can prove the minimum modulus principle. So in that case, fz has no minimum value inside D. So the statement is almost similar. So what is the minimum modulus principle? So statement is, so statement of minimum modulus principle is, suppose f of z is analytic and not constant inside the domain in a given domain D, In addition to that, let f of z not equal to 0 inside D, then fz, then modulus of fz has no minimum value inside D, no minimum value inside D. So that is the statement. So we will prove this result by using the maximum modulus principle. Now since f of z is analytic within and on a D, so since f of z is analytic within and on a D and f of z is not equal to 0, since f of z is analytic within and on a domain D, and f of z not equal to 0. F of z is not equal to 0 inside D. So we define a function g of z, so which is reciprocal of f of z, right? Because it is non-zero. Now since it is analytic, so its reciprocal is also analytic. So that means g of z is analytic within and on a D, within and on a domain D. Then by maximum modulus principle, then by maximum modulus principle, by maximum modulus principle, since this is the analytic within and on a domain D, also since fz is not constant and g of z is also not constant, so not constant, so then we will apply the maximum modulus principle. It is analytic and not constant, so it implies 1 over fz, the g of z, this has maximum value on the boundary of T. G has maximum value on the boundary of D, so it imply its reciprocal, so which is a 1 by fz, its reciprocal f of z, it attains minimum value on the boundary of the domain D, on the boundary of the domain D. Domain D. So it has minimum values on the boundary of domain D. Also, we can say that it has no minimum value inside the D. So just remember the statement of maximum modulus principle. So what is maximum modulus principle? If the function is analytic but not constant, so it has no maximum value inside D. Similarly, if function fz is analytic, not constant, and fz is not equal to 0, then modulus of fz attains no minimum value inside the D. So this is very important result, maximum modulus principle as well as minimum modulus principle. Now next theorem is again very important. So what is the statement of that theorem? Suppose, so statement of the result, suppose number 1, there are some condition number 1, the function fz is analytic in a domain D defined by modulus of z less than r. It means it is a circle with center, origin and radius capital R. So this is statement number 1. So part 2, this function is bounded. First condition is analytic. Second condition is bounded for every z belongs to D. So in the domain it is bounded. And third condition is its value at 0 is 0. It means no constant term. So these are the three conditions of the theorem. If all the three conditions are satisfied, then so if all the conditions are satisfied, so then modulus of fz less than equal to m by r into modulus of z. Also, if equality occur for any one z, for any one z, in that case f of z, which is equal to m by r into z into e raised to power iota alpha, so where alpha is constant. So this is very important result. So if all the three conditions are satisfied, then it proves this result. So how we will prove this result? Now given domain is a domain with center, origin and radius capital R. So that is a given domain. So I take a some neighborhood inside that domain. So I take C, which is a circle modulus of z is equal to small r, where small r is less than capital R. So this is a circle inside the given domain. So what is the given domain D? So this is a point origin O, and this is a capital R. So this is a given domain, and what we take C. So C is a some circle inside this. So this is a C, and this radius is small r, this values. Now, since function is analytic in the given domain, so we can expand by Taylor expansion. If we can expand by Taylor expansion, so it implies f of z, which is equal to summation of a n z raised to power n is running from 0 to infinity. So this is equation number 1. So this is by Taylor expansion. So we write it in the form of Taylor expansion around the origin. So if I write it as Taylor expansion, so what is an? So an is equal to nth derivative of function at point 0 over n factorial. This is. Now this can be written as fz, which is equal to a0, a1z, a1z plus a2z square plus a3z cube and so on up to infinity. So this is my expansion of a function fz around origin. Now by part 3, so what is by part 3, f of 0 is equal to 0. So substitute z equal to 0 in this equation. So it implies the value of a0 will become 0. So it convert this function fz, which is equal to a1z, a2z square plus a cube z cube so on. So this z is common. So we get a1 plus a2z plus a3z square plus so on up to infinity. So in this way, I can write it as this form in the expansion. Now, this equation can be written as f of z over z, so which is equal to a1 plus a2z plus a3z square plus so on up to infinity, this values. Now if I write this function phi z, which is f of z by z, so clearly it is analytic. So clearly it is analytic, so it implies z equal to 0 is a removal singularity of function phi of z. So what is removal singularity? So just I explain. Now this, from this function we see that this z equal to 0, it means 0 is the singular point of this function. But we can expand this function in the form of power series. If we can expand in term of power series, then it means z equal to 0 is the removal singularity of a function phi z. Also, in addition to that, if I substitute the value of z equal to 0, so what is phi of 0? So this will become a A1 because other term will be 0. So phi of 0 is equal to A1. So this phi z of this kind, which is equal to A1 plus A2z plus A3 and so on, this is written as equation number 2 and this is written as equation number 3. So what we get? So clearly this function is analytic. So simply this function is analytic. Also because its value is equal to A1, so it is not constant. So we can apply the maximum modulus principle to this function, right? So what clearly this function phi of z is analytic and not constant in a given domain and not constant. It means by maximum modulus principle, maximum modulus principle, modulus of fz attains no maximum value, no maximum value. So here it is not fz, here it is phi z. So it attains no maximum values inside the C. So it attains maximum value on the boundary of C, not inside C. Ja is that on the boundary of C. So it is on the boundary of C. Assume it has maximum values at z equal to A. Suppose it attains maximum value at z equal to A on C. On C mean on boundary C. Then it implies modulus of A, the modulus of Z. What is that? This is a R and this is R means which is a less than capital R because small r is less than capital R. So we get these values. So it implies modulus of phi A which is equal to modulus of, just substitute the value of z over A, these values. So what is this? It is a maximum value of phi z, that is at point A. So this is less than equal to, because this is less than equal to m over r, because this distance is r and this is less than equal to m. So this is a less than equal to m by r. So this is maximum value of phi z which is m by r. So this value is phi a less than equal to m by r, right? Now, if z belongs to C, now if this z, it belongs to C, that is on boundary, if z belongs to C, inside C, in that case, phi of z, which is less than equal to phi of A, because it is maximum value. And what is this maximum values? Less than equal to m by small r. It implies substitute value f of z over z less than equal to m by small r. Now this value can be written as modulus of fz less than equal to capital M by small r into modulus of z. This values. So this is our equation. Now for equality, this value is f of z less than equal to m by r. For equality, for equality, so when there is equality, in that case, f of a, this values, which is equal to, because it is equality, m by small r into this a, and small r approaches to capital R. So it implies modulus of f of a, which is equal to m by capital R into modulus of a. So this can be written as f of a, which is equal to m by r. So this can be written as a into e raised to power iota alpha ja iota lambda. So this is e raised to power iota lambda. Ja, we can also write it as iota alpha. Now this can be written as f of z, if we replace this z, m by r into z, where e raised to power iota alpha for z in C, for z in C. So in this way, we can find the value of f of z in case of inequality. So this is my result. Now the next result, which is called Scavarge inequality, Scavarge lemma. So that is based on this theorem, Scavarge lemma, that is based on the previous result. So what is the statement of Scavarge lemma? The statement is, suppose this function number 1 f of z is analytic in a domain defined by modulus of z less than 1. In the previous theorem, it was capital R. So here it is 1. So it means capital R will be shifted to 1. Number 2, so what is second part? Modulus of fz which is less than equal to modulus of z. And third part, which is f of 0 is equal to 0. Then prove that f of z less than modulus of z and f dash z which is less than 1. Equality hold if f of z is equal to z e raised to power iota alpha, where alpha is real constant. So we will prove the previous theorem and just putting capital R is equal to 1. So to prove this Scavar's lemma, so we will prove by previous theorem just substituting capital R is equal to 1. So simply we will do capital R equal to 1, then we will get our result. So this is, if capital R is equal to 1, so this will be 1, right? So this will be 1 m into z. If this is less than equal to 1, so this is modulus of fz less than equal to modulus of z. Now again this r is equal to 1 and m is equal to 1. So substituting capital M and capital R is equal to 1, then we will prove the lemma which is called Scavar's lemma. So this is very important lemma. So in examination it will be asked as state and prove Scavar's lemma. So in this case, in the previous theorem, we will just substitute the value of capital M which is equal to 1 and value of capital R which is equal to 1. Then we will get the proof of Scavar's lemma.